Okay, so sorry about little bit being late. Uh, can we see the finally? So to see this question one is familiar because it's like already we have seen this step. Because there is a square or power 2 in the derivative, the only appropriate method that we can apply and solve this is just y equal x prime. You have seen in this one in the exercises and also in your mid semester exam as well. So we do this. This is the simpler one. So y prime, we are able to obtain this x dash as well, but actually I should have started from x double dash, rather than starting with y prime. So this guy will be y prime plus y squared. So from here, you see that what I have written for you is just we can solve this equation because it's separable. So I obtain this guy. So I obtain this y as 1 over t plus c1. Since y was equal to, actually y prime was equal to x, sorry, since y was equal to x prime, so x will be log of this guy plus new constant. And also we were able to obtain the equation by assuming this minus x prime rather than positive plus x prime. So we can do the same job and obtain xt, but instead I can obtain minus log, but it is the same as this one except minus here. And actually I can put c2 here, or however, or maybe I cannot obtain it. So anyway, slightly different. Okay, but I doubt if they are independent. All right, so now this was part A. So part B tells me that are there any other special solutions? So the special solutions can be we can somehow obtain, maybe see, x prime can be c. So if it is c, this will be 0 and this will be 0. So the both sides of the equation will be 0. And also if I take this xt log t plus c1. So this can be another solution for this one as well. Okay. So see that t plus c1, okay, it's the same as it. So actually that's the other solution, this guy. And if I want to verify this solution, what we have obtained, I can just take this and take derivative and double dash second derivative and sub it in the equation. We will see that it is 0. The same story can happen for the other solution as well. All right. Question 2. Okay. So it's not homogeneous because of this one. But if there was no one, xy dx, x squared dy, it could be considered as a homogeneous ODE. So we can show that this ODE is not exact. Okay. So I like these notations, mxy dx and xy dy. So if this m, so m's partial derivative of my or del m del y, so it will be the partial derivative of this guy in terms of y equal to x, partial derivative of this guy, partial derivative of the terms, which is the coefficient of dy in terms of x, the opposite derivative. Okay, this is way that maybe you can remember. So we can obtain this one. So we can see that x and 2x, they are not equal generally. So we have to use the integrating factor, which, okay, let's have a look at the cheat sheet. Okay, we can obtain the cheat sheet from this one. So anyway, my minus nx is the same as same. So my minus nx will be 2x minus x minus 2x. So I will have minus x. So I will be happy if we can just divide it by n. So since we can just divide it by n, I conclude that my integrating factor should be this guy, mu of x, exponential of this guy here. All right, so from here, I just sub nothing interested here, and we can obtain this guy. All right, so this is 1 over x or 1 over absolute value of x. So integrating factor can be 1 over x or minus 1 over x. So anyway, multiplying this by in the ODE, 1 over x, I multiplied by here. All right. So my n will be updated. So my 1 over x, so I will have this guy. So if I analyze this one, so derivative of this guy in terms of y is 1, derivative of this guy in terms of x will be 1. So it is exact. Now solve the equation. Fx, this guy here. So okay, so when this equation from the first, it was like this. So we take total derivative. Total derivative will be del f del x dx plus del f del y dy equal 0. So this is this guy. So this means this, if we have this one, it means exact ODE. So you can see if you take derivative in terms of y here, derivatives in terms of x. Since this is continuous, so we can commute del y del x. So these will be together equal. Now, so this is the exact version. Okay. Now we come here. So fx is, it's not that one, it's updated one here. So fx is this guy here. So this is del x dx del f del y dy equal 0. So I see this guy here, del f del x. So they propose to obtain f. f is equal to log, so derivative integration of this one in terms of x. So this guy log absolute value of x plus xy plus gy. So you know that why we write gy. You are now professional. Del f del y is fy. So you've got this one to the if you take a derivative in terms of x, this will be 0. So it's the most pessimist general constant. Okay, in terms of x, this is constant. Now, you want to obtain gy, how we can use this second assumption here, use this one. So now del f del y equal to fy x y x. So I take a derivative this guy in terms of y, so this x plus g prime y. But del f del y is equal to x. So I put equal nxy, it's the updated version, x. Cancel, g prime y, thank you very much, 0, g y c1. So f is equal to this guy plus c1 or this y equal to c. You don't believe me that, for example, in marking scheme, it was like obtaining this 1 mark and writing this one half mark, James McCoy. Okay, so, but I tried to avoid this part, but try to write this time. Okay. Also, please note that just use this method. If you use other method, you won't get marked. Thank you very much. Solve this one by what? Okay, so we see that we rewrite that 2 is here. We write it in this way. So we see that dy dx is equal to this guy, which comes from this guy. So we like to write in this way, decomposing the fractions. So this comes here, and this will be first order linear ODE, okay, which is just like kindergarten. So you don't need to know these because you know already, although I have written it. So this will be the same as this guy. But integrating factor is, since I put x, so I should put, I don't need to put absolute value of x. But anyway, so, but there is absolute value of x here. So maybe we should put absolute value of x as well. Anyway, when you have integrating factor is like something like absolute value of x, then you are free to choose your integrating factor as just x or minus x. 3. So you will get one questions like something like this. You will get a question that then you will have to use Cayley-Hamilton theorem. Thank you. Cayley-Hamilton theorem. So, but you can solve these things by using classic methods, but sometimes it seems that Cayley-Hamilton is faster. Anyway, so this is like this one, so I can write this one is like 2x for y, 2x for y, and 0x minus y, 0x minus y. Critical points is I'm just unable to see that y is equal 0, so then I can obtain x equals 0. So this is a unique solution because if I write this guy in terms of like with using this notation, this system of equations has got a unique solution if and only if this determinant of the coefficient is non-zero. All right. Part B. Where is the part B? Yeah, part B. Determine nature of the critical point. 0, 0. So the eigenvalues of this guy 2, 4, 0, minus 1. So the eigenvalues are 2 and -1. Okay. So lambda 1 equal 2, lambda 2 is equal -1. So this is a saddle point. Okay. So one of them is like this and one of them is like this. So and at one side is that last week's and 2 weeks ago, if you go to that website, try to see to plot the vector fields or phase plane, you can see that the critical point will be saddle point. So in one way, some way, it is tending to the 0, and in some other in the other routes, it goes to the infinity. It escapes from critical point. It's saddle point. Do you know the meaning of saddle? Sat on the horse. Yeah. Yeah. Okay. Yeah. So okay. C. It says that so to be able to solve this one, so you don't have to write this guy here. You can see that one of them is real, one of them is positive, one of them is negative. So it is saddle. But we know that if you want to solve this, it is like xy. So eigenvectors of this guy, eigenvectors of this guy. So so you can solve it. But if you don't like that method, we can use Cayley-Hamilton. Okay, so the Cayley-Hamilton tells us that exponential of AT is like this guy. So, but instead of the matrix A, okay, you can substitute instead of A, eigenvalue. So, we use this guy and we see that we had two eigenvalues, 2 and -1. So e to the 2t minus equal to alpha 0 times 1 this time, 1 plus alpha 1 times 2 here. And the same thing happening e to the minus t, this guy. Now, if you have one eigenvalue, similar eigenvalue, okay, what you could do was this. Writing, so you have one eigenvalue, so you have this guy here. Then you can take a derivative and make it as a second equation. So you will get system of the equation. Now, anyway, so since you have two eigenvalues, you don't have to think too much. Okay. So we write this one. So again, so what is this? This first equation minus the second equation. So I will get this equal to this guy minus this guy. So alpha 1t is this. So it's like nothing interesting here. Alpha 0 is this guy. So therefore, we can see that the ODE will be like this guy. E to the 80 times constant, but we can obtain the constant. The constant tells me that if t equals 0, so we can see this one. So if t equals 0, this will be 1. So x of 0 will be this guy. So this is really a constant. You know, in one dimension, that if it was like x prime equal to 2x, then the answer is x equal constant times e to the 2x. Then we had that constant like there. Now e to the 80 is like this. So this. Okay, this guy, this remembers me Kosh. This remembers me Shine. So I can combine these matrix. So okay, did I do this really? Okay. Okay, x of t, c times e to the 80. So x0 e to the 80. So it means this x0. So why I do right here? Because I cannot multiply from the left. So it should be written like on the right. So that's why I have written it here. So because this will be 2 by 2 matrix and this is 2 by 1. So it's multipliable. All right, what else do we have? Okay, so we don't have anything interesting. So I have this, multiply it, e to the 2t, e to the minus t. Okay. So I separated e to the 2t. There is no e to the 2t here. So that's why this will be 0. E to the minus t, e to the minus t, and e to the minus t. So y0, y0. Okay, so verify that the solution in part D using the alternate approach to construction of the solution via the eigenvalues. So as I said, this is the eigenvalues 2 minus 1. So I can obtain eigenvectors v1, v1. So I'm gonna obtain, so this from here, so I can get this one. So I'm gonna find v1. So I can write this one. So from here, we see that these guys, this will be, I can divide it by 4. So this will be 1. And so then I can make this one 0. So as a result, from here, 0 times v1 1 equal to 0. 0 times v1 1 plus 1 times v2 1 will be this guy 0. As a result, this will be 0 from first. And this will be 1 times v2 1. So v2 1 will be only the left side here will be equal to this 0. So v2 1 will be 0. v1 1 can be anything. But since we like 1, we will put it 1. So v1 is 1 0. Do you have a question about this? All right. So if lambda is this guy, so you can obtain the second eigenvector as this. So x5 will be 0, 1, 0, e to the t. So this guy. Congratulations. So if I choose c1 to be like x0 plus 4 over 3 y0, c2 equal y0, then I will get this answer. So see, minus 1 4 over 3 and 1 here. So it looks like this c2. This guy. So it means c2 should be y0. Anyway, see, so this verifies that the previous method is right. If I have instead of x of 0, y of 0, this means time equals 0, x0, y0. x0 is 1, y0 is 1. So the solution, so I don't need to think too much. So I just sub x0 by 1 and y0 by 0. Okay. G. So since you didn't have this question in your mid session, and you didn't have this question in the, where was it? assignment. Okay, so you will have definitely this one. So in the last years, in the second assignment, there was this question, but James just didn't just made the second assignment like out of 60. Last year it was like out of 32, something like that. So, and the first question was this, and the second question was programming. But anyway, XP. This guy is non-homogeneous. So therefore, you've got an EAT and one XP. So it has non-homogeneous part. So we obtained the homogeneous part, e to the AT, but we've got non-homogeneous part, which is this. We can obtain XP like this. XP. So XP this is the formula for XP. So what I don't like here is just whole thing. But anyway, we don't have any choice. We should cross it. So integrand here, e to the minus a s f s, e to the minus a s f s. Means this guy, we have obtained it already. Remember that instead of t, we substituted by minus s. So that's what I made a mistake when I was writing. I just subbed s instead of just t. So I should have substituted by minus s. Fs is this guy, e to the t, e to the s. And minus e to the t, minus e to the s, 2s. So anyway, the rest is just multiplication of this guy. And then what? I haven't written this one. Okay, so you will do it. But maybe I can do it after this class and I can write it down. So it's obvious what you do. So this multiplication here, integration and integration from 0 to t. Actually, I wrote this one, but because this mistake here, instead of s minus, I just put positive s. So what? So everything was mistake. So I was just not happy. So I erased everything and I didn't have time to write again, to rewrite. So I can obtain this, integrate element twice, then multiply by this. So then I will obtain xp. Therefore, this question asks us to obtain the xp. But anyway, the general solution will be xc, the homogeneous part, plus xp. So this guy, they write the homogeneous part, but for the homogeneous part, xt, xp plus this guy. And the homogeneous part comes from 1, 0. Now, this guy. Homogeneous part is the something, but we have a particular condition for the constant or x0 and y0. So we apply that and we obtain. This is the homogeneous solution. You might ask that why x0 for obtaining particular solution in homogeneous part, you don't need xp. Okay. You remember that in Green's method, Green's function, actually, when you had boundary condition, you were able to find C1 and C2. I'm talking about IVP, initial value problem. If you were using Green's function for obtaining YP or particular solution, you could obtain C1 and C2 without YP. If you were using Green's function. However, if you use the classic method to obtain YP, then you obtain yc, then you obtain yp, then you are going to choose, you are going to find C1 and C2 using both yp and yc. But here and Green's function method for IVP, you don't need yp or xp because it will be 0. Why is it 0? Xp, look at the in time equals 0, xp, this, if I apply 0 here, then this will be 1, then this will be something, whatever, integral from 0 to 0. So this will be 0. Okay. That was a side remark. All right. Question 4. So you know forward Euler method. Forward Euler method is good for, and it is easy for implementation. But we have backward Euler method. So yn plus 1 yn plus h times. There is a difference between you guys and those ones that study engineering but not appropriate mathematics courses. The difference is this. Forward Euler method, yn plus yn, implement stage MATLAB. Oh, good luck. But it is like, it's apparently it's fancy, but intrinsically it is nothing. Okay, but forward by Euler method, you see that yn plus 1 is only here, and you can obtain from previous one, and it is explicit. Backward Euler method or implicit Euler method, yn plus 1 is here, yn plus 1 here, and xn plus 1. In fact, it is h times f of xn plus 1, yn plus 1. Okay. Forward Euler method, you remember that in week 10, okay, you had, for example, I did SageMath, optional SageMath files. You can see there that, for example, y prime equal, let's say minus 3 times y. So y prime, let's write this one. We obtained that, we proved that in question 2 of week 10, that the step size that you can use for the forward Euler method must be less than 2/3. And I did 2 numerical examples in the optional Sage file. For example, I did h 0.2 and I did h 0.7. Okay, and I saw that h equals 0.7 for, let's say, starting y of 0. Let's say 5 times 7 tenths, it will be to obtain 3.5. So we have, and if you use this h 7 tenths, if you kill yourself, you cannot converge. Okay, whatever you do, you won't be able to get the solution. But 2/3 is 66. But if you use like 6/10 or less than that, 2/10, your solution will be convergent. Now, I want to say something. Implicit Euler method. So we are completely off. Yes.
Where's the h less than 2/3 come from?
It's question 2, week 10. We had this. Do you remember something like p polynomial lambda times h, and this polynomial lambda must be less than 1. So if you write, so say we have simple example here. If you write several times y, so this will be yn plus 1 equal yn plus h times minus 3 y. So if you write this one, then you will have y0 times 3 minus 3, say n times h. Okay, so it will be like this. So from here, we had this guy that h anyway, so I don't remember exactly, but I have it in my handwriting. Question 2, week 10, question 2. So, okay, we saw that h must be this. Okay, it's exactly, it's written there. I remember something like h less than 1 divided by lambda divided by 1 plus sorry, 1 plus something. Okay, 1 plus lambda. It is there, clearly it is written. Okay, so you should have that one. But this is the say this it states out that we can choose for h is very risky. This is the drawbacks from the drawback of the forward Euler, but backwards Euler method or implicit Euler method. So see, after solving this yn plus 1, then your work is to obtain yn plus 1, which is this side and this side. So you need to solve it, for example, using Newton method. It's annoying, okay? But what is the advantage of the backward Euler method? You won't have this restriction. You won't have this h less than 2/3, for example. Okay, so this guy, you won't have this one. Actually, the space that backward Euler method, which is convergent or stable, is complement space of this one. So I believe that this should be h can be bigger than 2/3 for backward Euler method. I didn't see this proof and I didn't have time to prove it, but it is like this. So forward Euler method, two things. It is implementation easy, but we are worried about the step size. It should be small enough. But backward Euler method, it is slow, lazy. Why? Because you need to do solution, solving the yn plus 1 in any for loop. You need to do a Newton's method, for example, to find yn plus 1 because it's implicit. It's 1 here and it's 1 here. Then next step. So it will be very slow, but the stability is high in backward Euler method. Oh. Okay, RK2 is this guy. Yn plus 1, yn plus h times k1 plus k2. K2, it is K2, sorry, not K1 plus K2. K2 and K2 is f of xn plus h over 2. And it's this. So it's just, I just copied from the course note. All right, part B. This guy, approximate this guy. So you can do it by yourself. See, I give some opportunity for you. Part C. Show that backward Euler method for this problem is unconditionally stable for any lambda. So there is for less than lambda, it should be less than 2/3 in forward Euler method. But we can see that here there is no condition such like that. Yn plus 1, yn, this guy. So h distribution h inside the parentheses, I get this yn plus 1, this guy, and yn plus 1 is obtainable like this. All right. So what I did here, instead of xn plus 1, I just did xn plus h here. Okay, to say that this really works, if I if yn, one way is this. If yn is added by something, then yn plus 1 should be added by something else. Okay? Is it obvious? If yn changes, yn changes as which I have written it here, yn plus 1 should be changed. Okay? So epsilon sub n plus 1 is epsilon sub n plus 1 will be equal to this guy. Epsilon n, this guy, this fraction. So now I will have this one. This is stable if 1 over h is less than 1. Do you remember that in polynomial? So I wrote that yn should be polynomial lambda times h. This p of lambda must be less than 1. So here we should have this one, but this one lambda is less than 0 and h is bigger than 0. So this minus here, it means h lambda is always positive 0. So 1 plus something positive. Okay, so this is always right. So for lambda less than 0, there is no restriction for h. Whatever you like, just sub it there, and backward Euler method or implicit Euler method will work. If you so again, week 10 optional sage files. Okay, so part D, error analysis we have done already. You don't need. Okay, this guy. So I just copied from the course notes. Week 5, x squared y squared. How to obtain the critical points? It must be 0. 0 here. So 0, 0. So y0, x will be plus minus 1. So Jacobi matrix or derivative matrix for this one, we have talked about this. So this will be 2x, 2y. So I just obtained from here and here. Do you want me to explain this? C, F, D, F is df must be where f is from 2 dimension goes to the 2 dimension. Okay. df is equal to for f r, a function from r to r, the derivative is single number. F of x squared is 2x. For f from 2 dimension xy goes to the 2 channel. 1 channel, second channel. Okay. So f of xy this times is f1, f2. So f1 del f1 del x, del f1 del y, del f2 del x, del f2 del y. Okay. So we've got this one. So with using this Jacobi matrix, we will do some analysis. So Jacobi matrix is just obtainable here. There are 2 critical points, y is 0, so x equal to plus minus 1. So I can sub it here. So nevertheless, this Jacobi matrix has got 2 eigenvalues. Since it is a triangular matrix, so diagonal members are the eigenvalues 2x, 2 delta, 2 delta, 2x. So at this critical point is lambda is minus 2 because I just sub x equal minus 1. At this critical point, I just sub x equal plus 1. So it will be plus 2 delta. Delta 2 delta minus 2, you can interpret very easily. If delta is less than 0 and this is already less than 0, then it will be attractive. Otherwise, it will be saddle. Positive delta is positive, then it will be non-attractive, unstable, or If delta is less than 0, then this will be saddle. You can do the rest by yourself. Part C. Oh, okay. We don't have time. Do you have class here? No? Okay. Yeah, so
They've been released on Teams, right?
yes.
They go.
Part C. Okay, part C and D. It is really okay. See, obviously, see, I was shy to write all of the details. Okay, because you are already smart. Obviously is this. See, y prime equal to delta t, it's like e to the 2 delta t. Okay, so you don't need too much. Okay, and this guy. And you can do the rest. Delta is less than 0. This will be okay. Let's go. Thank you very much for being in this course.
Yeah.